working through problem 3.32 from Taylor's Classical Mechanics. This is a problem calculating the moment of inertia of a sphere. It's a uniform solid sphere rotating about its diameter. And we're going to replace this sum to integrate over it and find out what the moment of inertia of a sphere, a uniform solid sphere, would be. To do this, we're going to need to use spherical polar coordinates. dv is going to be r squared sine theta, dr d theta, dphi. And another useful thing is that p is r sine theta. Now, the way you may have learned this in calculus is actually reversed. Theta will be phi, and r will be p, and vice versa. Now, I'm going to solve this the way it's given here in the problem. I'm actually more familiar with the other notation myself. So, if you are, feel free to solve it that way. You'll just end up with 2/5 mp squared. So, to begin with, we need to find the density. When we're working with 3 dimensions, our density is going to be mass over volume. And our density in this case is going to be m, is our mass, and our volume is 4/3 pi r cubed, which is the volume of a sphere. So our density is going to be 3m over 4 pi r cubed, and that is our density. To begin with, we have our integral. It's going to be our density, r squared dv. That is going to give us our moment of inertia of the sphere. In this case, our density is 3m over 4 pi r cubed, and our dv, make this just a single integral for right now, just to represent what we're doing. Our r squared is actually going to be p squared, and our p squared is going to turn into r squared sine squared theta, and our dv will turn into r squared sine theta dr d theta d phi. (3m over 4 pi r cubed). And we're going to integrate our phi from, this is what you would usually be calling theta if you're in a calculus course. That's most likely what you will be using, from 0 to 2 pi. Integrate our theta, this is usually phi, from 0 to pi. Everything gets reversed when you get into physics, so it actually gets quite confusing just to work through a problem like this. That's why sometimes it's easier, use what you know. When our r is going to go from 0 to r, the radius of the sphere. So, when we work out this dv right here, we're going to end up with r to the 4th sine to the 3rd of theta dr d theta d phi. Working down here, 3m over 4 pi r cubed. We can pull that out because we have a uniform sphere. If our density was varying, that would not be able to happen. But having a uniform solid sphere, we can pull our density out here. We're going to go from phi equals 0 to phi equals 2 pi. And I'm actually going to write that out front here. So I'll first evaluate this r to the 4th. It's going to be 1/5 Plug in our r up here, we'll get r to the 5th, and that 0 will give us nothing. So just go down here from phi equals 0 to phi equals 2 pi. Then from theta equals 0 to theta equals pi of sine to the 3rd. We can write that as sine squared. Sine to the 3rd theta equals sine squared theta sine theta. And we know sine squared theta is 1 minus cosine squared theta. Sine theta, d theta, d phi. This allows us to make a substitution. That substitution being u. You can use whatever variable you'd like for the substitution. Just using u here, equals cosine theta. Differentiating, we get du equals negative sine theta d theta, which gives us negative du equals sine theta d theta. Alright, plugging this back in, we can go ahead down here. Going to go ahead and combine some things. We're going to have 3 over 20 m r squared over pi. And then we're going to have from phi equals 0, phi equals 2 pi. This time we're going to have u, we're going to plug in our bottom limit, change our limits of integration. 0 is going to be 1. We're going to have that negative though actually, so I'm going to go ahead and flip our limits in the same step here. I hope that's not confusing. We can have this negative out front, so I'm going to flip our limits of integration. U equals, we're going to use that 0 up here, so that's just going to give us 1. We're going to use pi, we're going to get negative 1. And that gives us 1 minus u squared du d phi. That's often a side note over here, just keep it slightly organized. I'm going to work down here, 3 over 20 m r squared over pi. And phi equals 0, phi equals 2 pi. And we're going to have u minus 1/3 u to the 3rd. And that's going to be evaluated between negative 1 and 1. And then d phi. So that's going to be 3 over 20 m r squared over pi. We notice that when we do this, we're going to get 2 times the evaluation from 0 to 1. So you can pull out a 2. We're going to get 1 minus 1/3. And then phi equals 0 to phi equals 2 pi d phi. And we're nearly there. 20. That's going to be 2 times 2/3. It's going to be 4 over 3 m r squared over pi. This is just going to evaluate out to 2 pi. You notice we're going to have some pi's here that go away. We're going to be left with m r squared. That's going to be, the pi's will go away. We have 3 times 4 times 2. That's 24. 20 times 3. If we're smart, we could have eliminated the 3 there, but I'll show you here. 60. And divide both of these by 3. Just to start, if you don't see it right away, that's 8 over 20 m r squared. Divide both of these by 4. Top and bottom of that fraction, you're going to end up with 2 over 5 m r squared equals the moment of inertia for a sphere of a uniform solid sphere. Has uniform density throughout. That's going to be your moment of inertia. That's where that comes from. You don't need to derive it. You can remember it, but it's good practice to know where it comes from.